Okay, so thanks, Chris, for the nice introduction. And it's been a great pleasure to, back here again after several years to introduce our most recent research progress in ISAC. So today my talk will be entitled Random Signal Processing for ISAC, and this is this work was supported by the National Science Foundation of China and Prof. Okay, so here is the outline. I will first talk about a little bit of the background and motivation. And then we'll look at two major signaling design, which is the MIMO and OFDM, two cornerstones of our today's wireless communication systems. And then we will show how ISAC signals can be designed under these two frameworks. Okay, and then we'll finally come up with some conclusion. So some background on ISAC. I think I will not, spend too many, elaborate on too many details here. I just, like Chris just mentioned, ISAC now has already been recognized by the ITU as one of the 6 key usage scenarios for 6G. So it is becoming more and more important. Now let's look at the motivation of my talk. So if we're going to implement the ISAC in the future cellular networks, we should first look at the current communication standardization, or let's see, the 5G NR waveform. And so if we look at the 5G NR, we can see that most of the existing technology using 5G NR-based sensing, they exploit the physical layer reference signals for sensing, so which are known as the pilot signals. So there are many these kinds of signals like CSI reference signals, demodulation reference signals, phase tracking reference signals, and they are all well-designed pilots with good ambiguity properties like autocorrelation properties. And these techniques, they are very easy to implement, but they are far from optimal. Why is that? Because if we look at the frame structure, we can see we have laser here. So it is a... Yeah. Oh, okay. Yeah. So you can see that the reference signals, they only occupy 10 to 15% of the time frequency resources, right? So if you look at a typical 5G NR frame structures. So that is to see the data payload, which occupies more than 85% of the resources. They are not fully exploited. So we know that for sensing, the bandwidth and the time duration are very important. So we have large bandwidth, then we will have good range resolution, and if we can accumulate more time resources, we'll have more higher Doppler resolution, right? So if we wish to improve our sensing performance, we need to employ the remaining 85% of the resources which are occupied by the data payload. So how to do that? Now, if we look at the data payload signals, it is very different from the radar waveforms. So we know that in communication, we need to transmit random signals because only random signals convey information. This is, from the theoretical point from the information theory, right? But if we look at the radar systems, typically radar systems employ well-designed deterministic signals for sensing, like phase-coded sequences with good ambiguity properties, or like the typically employ the waveform, the chirp waveform. They're all deterministic. They didn't contain any information there. So to convey information, the communication data signals have to be random. For example, we always in many communication model, we always assume that we're using Gaussian signaling or Gaussian codebook. Or in a more practical systems, we use QAM, PSK modulation formats to convey information. But if we're going to use this kind of random signals for radar sensing, we can prove that this will lead to performance degradation compared to the deterministic signals. Okay, so basically, in our recent theoretical work, we can prove that the sensing optimal signals should have a sort of constant modulus properties. This is also fully aligned to the radar theory that the signal should be constant modulus. Okay, so now let's look at the first scenario, which is MIMO. We assume that we have a MIMO ISAC base station with NT transmit antennas and NR receive antennas. So that means the transmit and the receive antenna arrays, they are separated. So the receive antenna is to receive the equal waves reflected from the target, which is serving a communication user, which is again multi-antenna, and also detect some targets here. Okay, so basically we can model the communication, the radar signals, radar equal waves in this linear Gaussian model. So for communication, we transmit a dual functional waveform. This is an ISAC signal matrix with L snapshots, and it will be received by the communication user. So communication user receives this YC, and this HC is the communication channel matrix. ZC is the communication noise, and the reflective equal wave will be YS equals to HSX plus ZS, while HS is the sensing channel. And so you can see that this X should be dual functional signal that's used for both. Okay. So now let's first look at sensing with deterministic signals. So basically, if the signal is deterministic, it may have this kind of structure that X equals to WSD. Well, W is a beamforming matrix to be designed, and SD is a deterministic orthogonal training signal. So SD Hermitian over L is an identity matrix, so which means SD is orthogonal. And typically, we wish to design some sort of beamforming matrix to minimize the loss function for radar sensing. And this loss function may be potentially non-convex, so FWSD. And here we simply assume that we need to satisfy the power budget constraints. So W norm square is less than P, and P is a power budget. So to solve this kind of problem, we have many well-established approaches. And here we just focus on a very specific example, which is the linear minimum MSE estimator of the HS, which reads like this. Okay, so here to use this estimator to estimate HS, we have to assume that HS follows the Widen stationary random process such that its second order statistic is RH, which is a statistical correlation matrix. Should keeps unchanged. Okay, and then by using this LMMSC estimator, we have an estimation error reads like this. You can see that there's an XX commission there, and we have this RH inverse, which is the statistical correlation matrix of HS, and because due to the orthogonality of our SD, so we can get rid of the SD here. We just keep WW commission here, and there's an L here. So you can see that this goes due to the use of orthogonal training signal matrix. And if we're going to minimize this with respect to W, we have a very beautiful structure, which is the water filling structure in this W. Well, this Q is the eigenvectors, contains eigenvectors of RH, and this lambda contains the eigenvalues of RH. So this is from this very classical GSP paper, training-based MIMO channel estimation. And now we need to rethink this assumption because now we're going to use random signals to do sensing, right? So basically, if we're going to use random signals, we have to rethink this orthogonality assumption. Well, S estimation over L is equal to identity matrix. So you can see if it is random, for example, if we assume this L, every column of this L subject to some complex Gaussian distribution, then this assumption will no longer hold because now this SS permission will become a random matrix as well, right? So basically, if SL is Gaussian and SS permission should be a so-called Wishart distributed matrix. Okay, And only when this L is, significantly greater than NT, then this approximation holds in a asymptotic manner, right? So we can look at the approximation error of this estimation minus identity matrix with different antenna numbers. So you can see if we have, for example, 32 antennas, and we wish to keep this approximation error below minus 20 dB, then we will have to accumulate more than 4,000 samples to reach to this requirement. But this will definitely impose very high complexity in our design, because this is just a narrow band MIMO, and if you imagine that we have OFDM, we have multiple subcarriers. For example, in typical 5G standards, we may have 1,024 subcarriers. Then these samples must be multiplied to 1,024, and which will impose huge complexity in our design, right? So that means if we're going to use random signals to do sensing, we may need to do sensing using short frequency, not such large samples to do sensing. In that case, this approximation will no longer hold, and the randomness of this Gaussian signal must be taken into account. Okay, now let's look at another. If we are going to use sensing, do sensing with random signals, so what shall we do, right? So we have to define some new metrics. For example, if we again have a loss function for radar sensing FWS, and now since S is a random matrix, this F should also be a random function. And if we're going to measure the sensing performance, measure the average error, we have to take the expectation with respect to S, right? And we treat this as a sort of ergodic sensing metric. And this is very similar to the ergodic rate in MIMO communication. Well, in MIMO communication, you have random channels. Now in ISAC sensing, we have random signals, right? So we can treat this as an ergodic sensing matrix, which is a time average over the randomization of S. Now, if we look at the LMMSC again, we will get the ergodic LMMSC, which is the expectation outside of this trace of inverse. And then the general modeling will look like this. So if we're going to design a precoder, we have to minimize the expectation of the estimation error rather than a given instance of the estimation error. So we may come up with two ideas to design this W. One idea is the so-called data-dependent precoding. That is because we're doing monostatic sensing. So we know every realization of S at our base station. So this value may change adaptively based on the instantaneous value of S, right? So that is for the data-dependent precoding. It is a little bit similar to the so-called symbol-level precoding in communication. Now, another design is data-independent precoding, which means that this W remains unchanged, such that W is independent of the signal realization. So why is this also good? Because for data dependent, this W has to be designed for every instance of S. Now, we only need to design a W once for all, right? So this will have a significantly lower complexity and is more practical design that you can implement it offline, and then you just have one single W for this ISAC transmission. Okay. And if now we look at the MIMO communication rate, which is not surprisingly the log determinant, right? And because we are transmitting Gaussian signals, so we just have this formulation here, which is again WW emission inside of log determinant. And if we're going to design a W to minimize the sensing error subject to the communication rate, we will have this sort of problems. Well, this R0 is the required threshold of the communication QoS, right? And this FWS is our LMMSC estimation error, which reads like this. Now, let's first look at sensing only precoding. So if we get rid of the communication rate constraints, what can we get? You know that if we remove these constraints, we will get the maybe the performance bounds for sensing using random signals, right? Now, we have the first proposition, which is that these Gaussian signals lead to an algorithmic LMMC that is no lower than the LMMC based on deterministic signals. That is, the deterministic LMMC serves as a lower bound for the algorithmic one, for the ELMMC. So we have this figure. Well, we have 32 antennas, and we transmit Gaussian signals. And if we transmit deterministic signals, we'll get this performance bounds, which is the represented the lowest estimation error. And if we transmit Gaussian signals with different frame length, we can see that if we're using only 32 samples for sensing, then we'll get maybe nearly, let's see, 5 dB performance degradation compared to the deterministic one, right? And this is due to the adjacency inequality. So because you can see that this trace of inverse is a convex function of SS permission. So if you put an expectation outside that, you can use the adjacency inequality. And that adjacency inequality gives you exactly the deterministic LMMC, okay? So that tells us that if we ignore the randomness of the ISAC signal, and if we're going to minimize this deterministic LMMC, that is merely to minimize the lower bound, which may, leads to performance degradation compared to really minimizing the one that accounts for the Gaussian signals. And we can first look at sensor-only precoding with data-dependent precoding, right? So that means we can first take the numerical approximation of the algorithmic LMMC by leveraging n Gaussian signal samples like this. Well, if n goes to infinity, we get the expectation. And here, this Sn denotes the nth Gaussian data realization. And for this summation, we can actually, if we have a large number of n, we can actually try to minimize each of these terms in the summation, right? We minimize with respect to each of these Sn, then we'll get Wn. So for each Sn, we have a precoder Wn. And fortunately, this problem has a closed form solution, which so despite that it is non-convex, which reads like this. So it is very similar to a water filling structure, but it is more complicated. You still have the Q matrix here, which is the eigenvectors of RH, if you remember that. And the US, we need another, let's see the singular vectors, USN, which is the singular vectors of this SN matrix, okay? And we need another permutation matrix in between to, order the eigenvalues. And within this, this matrices, we have a water filling structure of the, let's see, the singular values, okay? So if we, for each of these SN, if we first do SVD and we formulate this precoder using water filling structure, then we can have a set of DDP matrices, data-dependent precoding matrices, tailored for each of these SN, and our ELMMC can be calculated as this. So apparently, the data-dependent design attains the minimum ELMMC because we minimize each of these terms in the summation, right? So then the summation can be minimized. And this, however, is with substantial computational complexity. Now, if we look at data-independent precoding, which is that for all the data realization, we just have one precoder once for all. So this will become a very classical stochastic optimization problem that will minimize the expectation of this loss function. And this can be solved by the stochastic gradient projection method, so which is usually used in deep learning. Right? We can also use different kinds of stochastic algorithms like the popular item, and we have also tried item in our design, which gives us some more rapid convergence performance. And finally, we get just a single W for auto realization of data. And we also implement some high SNR approximation of this data independent precoding because this expectation is not, we are not able to compute the closed form of this expectation. which, because it's this integral is very complicated and has no closed form. So we try to approximate it in a high SNR region, and which gives us this formulation, and which transform the problem to a deterministic problem. And we can see that this will give us, very tight performance compared to the numerical results in a high SNR region. And then this gives us the optimal structure again of the precoder in the high SNR region. Now this is the some simulation for the sensing only scenarios that our algorithms all converge in moderate number of iterations. And if we look at the performance comparison of the proposed design with the one that ignore the randomness of the data, you can see that from this figure that we can see the data dependent precoding will give you, let's see, more than 3 dB gain compared to the one that you ignore the randomness. And the data independent precoding give you, like, let's see, the 2 dB gain compared to the one that ignore the randomness of data. Okay. And we can also look at the performance comparison with the high SN region, and we also compare that with the deterministic versus random signals. Well, this one is the deterministic signal performance with the increase in total power, transmitting power. And our design may reach to the deterministic lower bound if L goes to, let's say, 256. This is in, I think, 32 antenna setup, okay? Now, we should also look at the ISAC precoding. We didn't impose the communication constraints for now, right? And we recorded problem formulation, which is to minimize this expectation of the sensing loss function subject to the communication rate. Again, we can propose different approaches: the data-dependent precoding for ISAC, the data-independent precoding for ISAC, and data-independent precoding for ISAC in the high SNR region. And in this case, we should first consider the data-dependent precoding for ISAC. But this will give us some problems here. That is, given us realization of Sn, if we're still going to design Wn, which is treated as a function of Sn, and then this may introduce additional uncertainty. That means, because now Sn is Gaussian and Wn is a function of Sn, then Wn multiplied to Sn may no longer be Gaussian. So if it is no longer Gaussian, we may not be able to use log determinant as a communication rate, right? But fortunately, we can prove that this formulation, while we take expectation with respect to W of this log determinant rate, is a lower bound of the capacity. So that means this guy is an achievable rate in a data-dependent precoding design, right? So that means if we are going to have, for example, this guy that is larger than some threshold, then the capacity is also larger than that threshold, okay? So again, we can still validate to use this the log determinant constraints, but remember it is no longer capacity. Now it is an achievable rate. Okay. So we look at this optimization problem. We minimize the every instance of this error, sensing error subject to the communication rate. And this problem is non-convex. We introduce some auxiliary variable here, and then we put this auxiliary constraints into the objective function as a penalty, such that we can use the alternative optimization method to solve it. I'm not going to introduce the details. And then the data-independent design can also be solved in this way. We can have the penalty inside of the objective function and do the alternative minimization. And then finally, we can look at the results. These are the convergence performance of our algorithms. And if we again compare to the design that ignore the randomness of the data, you can see that we have substantial performance gain in terms of both the communication performance, the achievable rate, and also the sensing error. So this is a trade-off between the communication rate and the normalized ergodic element C. So you can see that we have 1.5 dB gain in terms of the sensing error reduction and more than 3 bits per second per hertz performance gain in terms of the communication rates. Okay, so that is about the MIMO ISAC precoding. So we already see that we need to take into account of the randomness of the data if we are going to leverage the 85% of the resources to do sensing, and that is for MIMO. And now we should look again at another major, communication standard as the waveform, which is OFDM, and to look at how the randomness affects the sensing performance in OFDM and how to deal with such randomness. Okay, so there is also OFDM radar in the radar literature that, but however, in radar waveform we do not transmit random signals, right? So basically, in OFDM radar, we always design deterministic signals. But now, if we're going to do ISAC, we have to adopt random signals to convey useful information. For example, if we transmit quantum symbols at each of the subcarriers of the OFDM, then there will be data randomness. And this data randomness will result in the flag-treated side lobes. If we look at the ambiguity function of the OFDM's communication signals, right? So because now ambiguity function is a random function of our random data, so the side lobes will become random, and which leads to the missed detection of weak targets and the false detection of close targets. So here our aim is to seek for new degrees of freedom for the signaling design, such that we can adjust this sensing and communication performance. And here we're considering the input distribution of constellations, which here we're using the so-called probabilistic constellation shaping for ISAC. Okay, so now we look at the transmitted OFDM signal structure, which is like this. So this is, we have, let's see, the L subcarriers. So this is a single OFDM symbol, and the TP is the symbol duration, and this AL and phi L will be the amplitude and the phase of the constellation points, right? Okay, and these are random variables. So for example, if we look at a 16 QAM constellation, which is like this, conventional 16 QAM is a uniform distributed constellation, such that each of these constellation points is conveyed at a probability of 1/16, right? But now we are going to change the probabilities of all these constellation points, such that to adjust the randomness of our signal to play with the ambiguity function. And we have an assumption here that for this kind of constellation, which is symmetric, which is rectangular, we may have different circles, right? For example, in 16 QAM, we have 3 circles. And each of this circle, the constellation points will be transmitted at the same probability, but at different circles, the probability are different, okay? So this kind of rule evidently guarantees that the expectation of this constellation is 0, okay? And this is a very typical constellation design. And our signaling optimizing variable is the vector of the probabilities, okay? So this P, which is another degrees of freedom to design. And we should first analyze the ambiguity function for sensing, which is like this. Okay, this tau is the delay, this nu is the Doppler. And this is, so if we look at a single OFDM symbol, we can actually decompose the ambiguity function of this OFDM signal into 2 parts. One is the lambda S, S means self, so we call this a self-ambiguity function. And this lambda C means the cross ambiguity function. So the self-ambiguity function means that the ambiguity function of the same subcarrier and added together. And the cross ambiguity function means the ambiguity among different subcarriers. So we have this L2 doesn't equal to L1, right? And add them together, we get this kind of formulation. And because now this ambiguity function is a random function, then we have to analyze its statistical characteristics, right? We can derive its expectation and also the variance. So because we are assuming IID constellation, so at each subcarrier, the symbols are independently identically distributed, such that this self part and the cross part, they are uncorrelated with each other. So in this case, we can very conveniently derive the variance of the ambiguity function. Here we give you the results. The expectation of the ambiguity function is like this, okay? And the variance of the ambiguity function is actually the summation of two variances. One is the self-ambiguity function variance, and one is the cross variance because of the uncorrelated properties of them. And so you can see that if we look at this sigma s squared, it looks like this, and there's a very specific term inside of the variance, which is the fourth moment of our constellation amplitudes. Okay, so this is the fourth moment. And we can see that this sigma s is equal to 0 only if when all the constellation symbols have the same amplitude. For example, we're transmitting PSK constellation, then this term will be 0, but we still have the cross term. So PSK still will give you a variance, that non-zero variance of the ambiguity function. But compared to the COM constellation, PSK will give you better performance, right? It will have a way smaller fluctuation in the set loss. And if we consider, so this is the variance of the lambda c, which is like this. So this sigma c square has nothing to do with the constellation points. It's just a constant, value that is related to the subcarrier spacing and other parameters. So we can see lambda c imposes no effect on the probability constellation shaping design. So if we're going to shape our constellation, we're only carry about to minimize this sigma s squared here. And we can extend all this analysis to OFDM sequences, so multiple OFDM symbols, which will give you very similar results. I'm not going to introduce the details. Okay, so here, what our system metric, as you can see, we are going to minimize the variance of our ambiguity function. We try to control the fluctuation of the set loss such that we can have better sensing performance. Now, if we look at the communication metric, and we're transmitting an AWGN channel, we're going to use this mutual information as a sensing communication metric. But be aware that now we're transmitting QAM or PSK constellation. We're no longer allowed to use log 1 plus S and R as our communication rate. Then we have to use this mutual information, which can be computed in a Monte Carlo integrals like this. Okay, and this Monte Carlo numerical integrals, this is the entropy of Y, is a function of our input distribution Px. Okay, and here the Pym given X is the conditional PDF with the standard Gaussian forms. Now we are going to do our probability constellation shaping design, which is to maximize our communication rate and subject to a given threshold of the variance, which is actually a given threshold of the fourth moment, because we already see here that the variance is proportional to the fourth moment. And we have another constraint, which is the normalized power and the probability constraints. Okay. And this achievable information rate has no closed form expression, and we are unable to use the standard CBX toolbox. We have to employ this kind of transformation, and then this can be reformulated in a double maximization form. We are introducing auxiliary variable Q here, and then we are going to use the celebrated Blahoto-Arimoto algorithm, which is the algorithm to design the distribution of the signal. And then this is a two-step iteration. And then finally, we get this Px of the input distribution. And we can also consider a heuristic approach, which is that because if we're going to solve this problem, every iteration will need to compute the entropy in a Monte Carlo numerical integrals, right? But this will give you very high complexity. And here to reduce the complexity, we propose a heuristic approach to simply minimize the gap between the fourth moment and a given threshold of the constellation. Because if we look at the PSK constellation, you can see its fourth moment is exactly 1. Otherwise, if we look at the quantum, for example, 16 quantum, the fourth moment is approximately 1.32, okay? So if we try to scale our threshold of between 1 and 1.32, we may get a performance trade-off between PSK and quantum in both communication and sensing. And this is nothing but linearly constrained least square problem, which can be very easily solved. Okay, let's look at some simulation results. And this is the zero doublet size, which is the autocorrelation function of our 60 for PSK and 60 for quantum signals. And this is the one that average over many instant realizations. So this is the single realization of 16 for PSK and 60 for quantum signals. You can see that we have fluctuated set lobs, which is random. And we average out, then we get this kind of performance. You can see that 16 for PSK has significantly lower set lobs compared to the 60 for quantum, okay? So the maximum gap is nearly 14 dB here. And now we are going to apply our constellation design, the constellation shaping design of our approach. So you can see that the traditional constellation will have uniform distributed points, and these colors represent the probabilities. And by using our design, we will have different colors on different points. That means we are transmitting this kind of constellation points at different probabilities. Now, what is the performance? If we look at a very specific scenario that we are going to detect a weak target in the presence of the strong self-interference. So self-interference means the interference at a zero delay, right? So we have a very strong self-interference here. This set lob may mask the main lob of the weak targets here. And if we're using 60 for PSK, we'll be able to detect these targets here. And we're using the SOC bar algorithm to detect the target. And if we're going to use 16 for quantum, we're unable to identify these targets because the threshold is now higher than this targets. And by using the design of constellation shaping, we again, for 16 for quantum, we are again able to identify these targets again. Okay, so how about the systematic performance and also the communication performance? Because now we are changing the probabilities of each of these communication symbol points. We may be able to reduce the communication rate because the uniform distributed constellation will give you the maximum rate. And if you change the communication probabilities, you will reduce the communication rate. Now, if we look at the detection probability of versus sensing SNR, we can see that this is for 16 quantum and this is for 60 quantum compared to the PSK counterparts. You can see always our 16 or PSK constellation will give you the best performance, and the quantum uniform distributed quantum will give you the worst performance. And our design may trade off between quantum and PSK by changing the probabilities. And also our design may trade off between the PSK and the quantum communication rates by changing the probabilities. So if you look at this achievable rate, this green line is the 60 for quantum, and this blue line is the 60 for PSK. So in the highest region, they both reach to 6 beats per second per hertz. But in the moderate SNR, you can see that there's a performance gap between them, and our technique may trade off between these gaps. And finally, we give you the results of a direct trade-off between the achievable rate and the detection probability. That you can see that so this is the performance of uniform, let's see, uniform PSK. We have the best sensing performance, but worst communication performance. And this point is the uniform quantum. We have the best communication performance, but worst sensing performance. And our design can trade off between these 2 points. And also, you can see our design. So this red line is the optimized design. This blue line is a heuristic design. And the heuristic design already achieves the optimal performance. Finally, some conclusion of the take-home message. I hope I didn't exceed the time here. So we propose some new sensing metrics for the random ISAC signals For MIMO ISAC transformation, we use this ergodic linear minimum mean squared error. And for the OFDM, we do variance of the ambiguity function. And we reveal that the variance is proportional to the fourth moment of the constellation amplitudes. And we propose different precoding design and different constellation shaping design for random signals. And the advantages here is that we can more accurately characterize the performance of random ISAC signals, and we have new degrees of freedom to control the trade-off between sense and communication on the random signaling. And the conclusion here is that random ISAC signals deserve dedicated signal processing. So finally, here are some references. If you're interested, you can look at these papers. Okay, so that's all for my talk.
So, thank you very much, Pan, for the excellent presentation. We have time for maybe one quick question, one or two, depending on how long it takes. So do we have any questions from our audience here?
Please.
Thank you, Dr. Liu, for your great presentation. Could you go to page 19, please?
Yeah.
Yes. So on the figure on the left-hand side, you seems to have an error floor. Where does that come from?
Right. Yeah. Yes, that is very good question here. So actually, here is a typo. It is not 4 versus 3. It should be 3 versus 4. So the error flow here is because if we are going to use auto-filling structure, for the deterministic signals, you can see that we will only allocate power to the eigenvalues that is greater than some threshold. And if the eigenvalue is 0, you will allocate 0 power on that subspace. So if you have L less than NT, then your signal match, your SS transmission will basically become rank deficient, such that you will allocate 0 power on those eigenvalues in the null space. So that will cause an error flow because the errors on those subspaces will never be able to scale with SNR. I don't know if I explained this right. Yeah.
Okay, I see. Another question.
Yeah.
For data-dependent precoding, do you have any more obvious intuition on how that data would affect your precoding? For example, say if I plot the beam pattern of the precoding matrix for a specific data sequence.
If we're going to consider beam pattern, then this will be a very different objective function, because here our objective function is the estimation error of the channel, which is the estimation error of the LMMC estimator. So these are different tasks. In here, we are going to estimate our radar channel, but in your beam pattern design, you're going to formulate some beam patterns towards some targets, and this is a different objective function. But still, in the beam pattern design, you can employ this kind of data-dependent precoding. No problem, I think. Just change your objective function.
Yes, but what I'm thinking more is like how that data sequence would affect my precoding. For example, if I have a
so actually, if you consider beam pattern, then if you have random data, your beam pattern will become random. You cannot precisely control your beams because it will have random fluctuations. And by using data-dependent precoding, you may somehow control your beams, to be stable at some SNR level somehow. Yeah.
Okay.
Let's stop at this point. So thank you for the question. Thanks again, Pan, for and then let me call next Professor Stefano Busi to the stage. And then while he's getting set up, let me see if I can go his bio. So Stefano got his MSc and PhD degree in the University of Naples in 1999.